The topic for today's reading group is variational inference. This topic is covered in lecture 7 and 8 in the course. And in today's reading group, I will use the original course slides made by Professor Eric Xing, but I actually revised it a little bit and put on some annotations on my slide. Okay, so here's the content for today. So basically, we broke things into 4 sections. The first is a very high-level idea of variational inference. And then we will use the latent directional allocation as an example to show how this variational inference is used in an application. And then we will go to the practice of variational inference, in which we will introduce stochastic variational inference and the black box variational inference. And finally, we go with the theory of variational inference, in which we will include more mathematical details. Okay, so first, variational methods. Essentially, variational is saying that you can re-express a quantity you cared about by a solution of an optimization problem. So for example, there are many ways to express the eigenvalue of a matrix A. But now we consider it using a variational expression like this. The solution of this optimization problem would actually be the largest eigenvalue of a matrix. Another example can be now assume that we have a linear system of equations and we can have its closed form solution x star. But if we consider a variational method, then we know that this x star can also be expressed in this variational formulation, which is a solution of an optimization problem. So the reason why we want this variational formulation after we have the closed form solution is that in the closed form solution, due to this inverse operation, the complexity would be big O notation n cubic. But for the variational formulation, if we apply a conjugate gradient method, which is some certain method to solve this optimization problem, then we can achieve n square complexity, which is more efficient compared to the closed form solution. Then after we have this general understanding of the variational methods, now let's take a look at the high-level idea of variational inference. So there's a true distribution P that we wish to perform wish to perform inference on, but sometimes this P can be very complex, and so we can't really do that. Therefore, we want to approximate this distribution P with another distribution Q. And the variational inference actually assumes the existence of this P and Q, and also requires a way to measure the distance between these two distributions. This distance measurement is usually the KL divergence, which is of this form for continuous case and this form for distributed. This case for distributed for discrete case, and this form for continuous case. Okay. So in the later sections, we will cover the mathematics of variational inference in more details. But now let's first just focus on one example application, which is this LDA application. Okay, so first of all, we consider the steps that we should consider when having a new modeling task. So the important elements to consider includes the task, the data representation, the model, the inference, the learning, and the evaluation. So we will follow these important elements and introduce the LDA application step by step. Okay, so now assume that we apply the aforementioned steps to the task of text processing. Our downstream task would be doing the document embedding. And then we consider various models that have been used for the document embedding task. One is this bag of words representation. But the problem for this bag of words representation is that in this bag of words representation, only the count matters, and we do not have any any information about the words orders. So which is not good. Then except for the bag of words embedding, we also have other embedding models like the topic models. So here's the big picture of the topic model. We usually start with an unstructured collection, and we want to discover the topics out of it, and these topics can be used as access to define the new space, which we called topic simplex. And then we should note that I suppose if we have an unstructured collection of documents, and then if we first embed it into this word simplex, then by conducting the dimensionality reduction, we can move from this word simplex to this topic simplex. And here's a method called the LSI, latent semantic index. So the basic idea of this LSI is to perform a singular value decomposition to decompose a Word document matrix into 3 sub matrices, which is this word topic matrix W, the topic matrix, this sigma, and the topic document matrix D. And here we also put the topic models here so that we can see the connections between these two methods, these two models. So we can find that these two methods are actually very similar. They have a similar form, and algebraically, the only difference is the absence of this topic matrix. And then after seeing this LSI and the topic model, let's move to a more general model, which is the admixture models. So in this admixture model, we have some objects which are bags of elements, and mixtures are distributions over the elements, and then we have a mixing vector theta, which represents each mixture's contributions for these objects. And then when we want to generate the objects, so for example, we want to generate a document, then what we do is we first pick a mixture component from this theta, and then we pick an element for that certain component. And here's a graphical model of topic models. So suppose now we want to generate n documents, and then the process would be for each document, we first generate the topic proportions theta, from a prior distribution. So first step is to generate this theta. And then we generate words one by one in this document. And each word are generated independently. Then for each word, Wn, we first generate its topic, which is this Z. It should be a latent variable. This Zn should be generated from a multinomial distribution whose parameters are these theta. And then with this Zn, we can find the corresponding per topic word distribution, which is beta Zn. And then we generate this word Wn from the multinomial distribution whose parameters are these beta. So that's the process of generating a document. Then we should consider the choice of priors. So we basically have two different ways for this generating this document. So one is the LDA, which is the latent Dirichlet allocation. It is using a Dirichlet distribution. So the good thing about this prior is that since the Dirichlet distribution is conjugate to the multinomial distribution, so we can have a very efficient inference. However, it can only capture the variations in each topic's intensity independently. So it cannot really capture the correlations between topics. Another would be this logic normal. So the good thing about this logic normal is that it can capture the intuition that some topics are highly correlated and can rise up in intensity together. But it is not a conjugate prior, which implies a hard inference. So in the following, we just consider this Dirichlet prior. And if you're interested in this logistic normal prior, then you probably can check these two related papers. Okay, so now we already know what is the task, and we know what is the data representation, and then we know what is our model. So according to these important elements to be considered, then the next thing we should think about is the inference. Okay. So for this graphical model, we can see that this W is the only observation, and this is the observation. And this Z and theta and beta are all random variables. Then in the inference task, we actually aim to figure out all these random variables. Okay. Now we can write down the joint likelihood of all variables like this. Then like this. Then we would be interested in an inference problem like given the data for here, it's given this W. Then we want to inference the posterior of hidden variables. And then in the following, we consider using the variational inference method to do so. So first of all, we should know that there will be two commonly used approximate inference method, which are the variational inference and Markov chain Monte Carlo. So for today, we just consider this variational inference. And as introduced in the beginning, variational inference is actually to turn the inference problem into an optimization problem by introducing an auxiliary proxy, which is in this case a distribution QZ. We want this QZ to approximate the prior PZ. So Z here is actually representing all the hidden random variables. So then our objective would be maximize the lower bound for log likelihood. Then we can have these formulas. And the details about how we can move from here to the first the first equality is here. So here's the mathematical details. And finally, we can see that the objective is actually equivalent to minimize the free energy, which is this formula. Then let's go back to, so this is about the variational inference, and then let's go back to our previous practice case. So in this LDA case, we introduced before, we should note that it is hard to do this inference on the true posterior, this P beta theta Z given W. So we consider using a mean field assumption, which is a commonly used variational base. We will also mention it in the section 4 later. And in this assumption, we assume that all of these unknown hidden variables can be partitioned so that each partition is independent of the others. So in our case, with this mean field assumption, we assume this Q is fully factorized like this. And then we should also note that the mean field family usually does not include the true posterior. Then let's consider for each beta, theta, and z, they should be parameterized by additional so-called variational parameter. Then we choose the approximation distribution like this. We choose the Dirichlet distribution to approximate the distribution for beta k and theta d, and then we choose the multinomial distribution for this z d. Then what we do is we consider minimizing the KL divergence to learn the parameter of the variational distribution. And we should note that for the LDA, we can actually compute the optimal mean field approximation in a closed form in a closed form solution. Then we consider for the LDA, we first would have these two distributions, which is a Dirichlet distribution for the topic proportion distribution and a multinomial distribution for a word label frequency distribution. Then if we plot these two distributions into the update step, then we can obtain this Q theta D, which is also a Dirichlet distribution, and it is same as its prior. Then similarly, we can, this is how to update this Q theta D. And then similarly, we consider update the QZDN and the Q beta K. And then we can iterating these equations to converge and get the mean field approximation to the posterior distribution P theta Z beta given this W. And by following these above steps, we can take care of this theta D, this ZDN, and this beta K respectively. Okay. So here is the coordinate ascent algorithm to solve this LDA. In this method, we just repeat the process of updating Q theta D, updating QZDN, and updating this Q beta K. and we keep updating them until we finally converge, and then we can finish the process of solving this LDA problem. Then actually we can summarize this coordinate ascent method at a very high level, as shown in this slide. In this one, this is a very high level summary. So essentially, there were two types of parameters to updates. One is the local variables, which were parameters for the documents, and one is the global parameters, like this. And then in this algorithm, all the documents, we should note that all the documents are looped before updating the global parameters. And this actually will become a problem when there are too many documents. So the updating of the model will be very infrequent, and therefore it will be very slow. So we should consider solving those drawbacks. And then what we can do is separating the loss function into two different parts. One is the global contribution, and one is the per data point contribution. And then if we denote by f lambda as this expectation formula, and then we denote by gi lambda phi I as this formula, which is for each data point. And then we can simplify this formula into this form. And then we consider first optimize the local parameters phi 1, phi 2 until phi n. And we can let the optimizer of each data point to be this argmax gi lambda phi I. Note that in the original slide, here is a typo. And then we should note that the gradient of the one parameter lower bound L lambda would have this following form, which would allow us to use stochastic gradient algorithms and update the model more frequently for a better convergence. And once the global parameter, which is this lambda, is estimated, then each phi I can be estimated online if needed. However, the gradient of the lower bound with respect to the parameters will not be the steepest direction. This is because the parameters represent this is because we use the parameters to represent a distribution, but sometimes the distance between parameters is very different from the distance between two distributions. So for example, in this figure, we have two pairs of Gaussian distributions with the same two means. And then if we consider using the if we consider characterizing their distance with the parameters, we can see that their distance of mean is equivalent because the distance between these two, the distance between the mean of these two distributions and the distance between the mean of these two distributions is actually the same. But when we consider their distance, we consider the distance between these two pairs of distributions using the KL divergence, then their KL divergence is very different. So that's why we say that's why we say why using these why this and that's why we say the gradient of the lower bound with respect to the parameters will not be in the steepest direction. And we can actually explain more about this point. So the reason why this happened is when we use the gradient methods, then the objective function is actually approximated by a local quadratic second order approximation like this. Note that for here, for this quadratic term, we use a second order derivative. We use the identity matrix divided by some parameter t to replace this second order derivative. But these kind of approximation may not work for the distributions, and that's why this normal gradients is usually not in the steepest direction. And then instead to solve this problem, instead instead of using this normal gradient, we consider using something called a nature gradient, in which we usually use the Fisher information matrix for the gradient, since the variational distribution is in the exponential family. And now after using the nature gradient instead of the normal gradients, then we can perform the stochastic variational inference by sampling the data points and then update the parameters using the nature gradient as shown in this algorithm. And note that we have derived variational inference specific for the LDA problems, but now we want to, instead of focusing on this one single example, we want to have a very general solution which does not entail the model specific work. So this solution can actually serve as a black box which outputs a variational distribution when the inputs when given any model and given massive data inputs. And this method is actually called the black box variational inference, BVVI. So in terms of this BVVI, there are actually two different types of BVVI. One is BBVI with the score gradient, and the other is BBVI with the reparameterization gradient. The later one is actually the foundation of the variational autoencoder, which is VAE. I think a lot of us is not unfamiliar with this term. And the variational autoencoder will be discussed more in lecture 12. So I think according to our previous schedule, it should be discussed in the next reading group. So for today, we will focus on the BBVI with the score gradient. So BBVI with the score gradient is that we consider a probabilistic model where X is the observed variable and Z is the latent variable. Then the corresponding variational distribution is this QZ given lambda. Then we consider its evidence lower bounds, and then we can have this formula. And then we derive its gradients and obtain this formula. So the derivation process is actually for here. We just follow these steps one by one, and then we can finish this derivation. So for here, I just skip the math for this part. And now we already have this gradient. Then using this gradient, we can take advantage of Monte Carlo to compute the noisy unbiased gradient of the elbow with the samples from the variational distribution. Okay. So that's So note that for here, we call this a score function. That's also why we call it a BBVI with the score gradient. And up till now, we have already seen how this variational inference can be viewed as an optimization problem in which we approximate the true solution by relaxing or approximating the intractable optimization problem. And now we want to kind of provide a unified view based on the variational principle. We should note that for here, for this unified, in this unified framework, we can consider two types of approximation. One is the loopy belief propagation, which acts as an outer approximation, and we also have the mean field approximation, which is an inner approximation. So in our previous LDA example, we actually consider this mean field inner approximation. So so thus far, we can see that the common inference problems usually include marginal distributions and normalization constant. But now we want to represent these two quantities. We want to represent this marginal distribution and the normalization constant in a variational form via the exponential families and convex analysis. So first of all, let's just recall this exponential family. So the exponential family actually described described previously in this course is this formula, and we have this theta as the canonical parameters, and we have this phi x, which is the sufficient statistics, and then we have this a theta, which is a log partition function. And then we should note that whatever the distribution p theta is, the log partition function a theta is always a convex function. This actually can be proved by its Hessian matrix. And there's also a constant for the domain of the effective canonical parameters that are the value of log partition function. A theta must be finite, like this. So for the exponential families, there are two examples. One can be the Gaussian MRFs, and the other can be the discrete MRFs. So both of them can actually be represented in the form of exponential family. So I just list these two things as two examples of that a lot of things can be represented in the form of exponential families. So we will not go to the details of them, but we should note that this exponential family is very important. And then we may wonder what would be the motivation of using these exponential families. So we should note that this exponential family is usually very useful because for the inference problems, we usually care about the margins, and then with these exponential families, those margins that we care about can be well represented, and then if we compute the expectation over the sufficient statistics given canonical parameters, and then we can already yield the marginals which we care about. And also, by the way, we should note that the sufficient statistics and the canonical parameters are duals, so which means that one can be computed from the other. And now let's consider an example. So we consider computing the mean parameter for a Bernoulli distribution. Suppose we have a Bernoulli random variable x, and then we can do the inference like this. But now we consider that we want to do it in a variational manner in which we consider casting the procedure of computer mean in an optimization-based formulation. So before we do this, let's first quickly go through the concept of conjugate dual function. This will be very important later. So the conjugate dual function is saying that given any function f theta, we can obtain its conjugate dual with this formula. So now let's try to understand what this conjugate dual function is actually doing. So now we have this curve, which is f theta. And then let's check the conjugate dual function. So first of all, we have an inner product of this theta mu. And then we can regard it as this kind of line. And then we can note that we use we find the corresponding value for each theta on this line. And then we find its value on this curve, and then we do a minus, which is to consider the gap between these two values. So essentially, we can find that what we are actually doing with this conjugate dual function is we are trying to maximize the distance between this line and this curve. And also we should note that one property of the conjugate dual is that it should always be a convex function. And also we should note that the dual of a dual is itself if f is convex and it's lower semi-continuous. So we should remember the dual of dual is itself. We should remember this formula. So in this sense, then in this sense, for the log partition function a theta, we can rewrite it under this. We can rewrite it this way under this domain. And in this way, then this dual variable mu would have a natural interpretation as the mean parameter. And now let's again go back to the Bernoulli example to see how it works. So first we know that the conjugate A star has this form. This is directly plugging the A function into the formula of the conjugate dual. And then if we solve this equation, then we can obtain this stationary condition. And then if we inversing this condition, like now we're representing mu with this theta, but if now we want to represent the theta with the mu, then we can have this thing. So this is to represent theta with mu. And then if we do this kind of inversion, and then we know this should be the form of theta star, which is the optimal theta. And then we plug in this optimal theta into the conjugation A star mu, and then we would have this formula. And then finally, using the dual of dual, we can solve the original partition function. And then we know that we have this kind of thing. And then we should know, then we should be able to obtain that the optimal is achieved at mu theta equals E theta divided by 1 plus E theta. And this is our mean. So this example of Bernoulli is It's just for the purpose of understanding how we use the variational representation. And then in general, the process of the variational representation should be similar in this Bernoulli example. So now assume that we are given the exponential family, then like this. And then what we first do is we compute its dual function, and then we get its stationary condition, and then we should note that these we should know that the derivatives of this A is essentially obtained as the mean parameters. Therefore, we can have this stationary condition, and then after we have this kind of stationary condition, we should be careful that this mu should actually be restricted to some certain domains. So we have to first assume that there is a solution theta mu. So there might not be this kind of solution. So we have to because there might not exist this kind of solution because we have some restrictions for the mu. But now we just first assume that there's this solution theta mu. Okay. So after we assume that there's a solution theta mu, and then we would have this mu equivalent to this expectation, and then we should know that this is actually derived by plugging in the optimal theta mu, and then use the definition of the joint probability of this exponential distribution. So that's how we compute this mu. And then recall that we have the entropy defined as this way. We should know the dual would be of this form when there is a solution. So we just plugging this thing into this dual form, and then we would have dual is equivalent to this thing. And we should also know that the solution would then be theta mu. So up till now, we actually provide a framework for general exponential families and graphical models. But there are still several problems we should note based on the current framework. So first, computing the entropy is generally intractable. And second, the constraint set of mean parameters would be hard to characterize. So for the later problem, for the problem that the constraint set for the mean parameter is hard to characterize for this problem, how we can solve this problem is by using the this marginal polytope. So for any distribution Px and a set of sufficient statistics phi x, then we should note that this distribution Px is not necessarily an exponential family. And then we define a vector of mean parameters like this. And then the set of all realizable mean parameters would then be a convex set. And when this Px belongs to a discrete exponential families, then this M is actually called a marginal polytype. And then we would know that the marginal polytope M would have the following convex Hall representation. And then by using the Minkowski-Weil theorem, any non-empty convex polytope can be characterized by a finite collection of linear inequality constraints. So now we know that the marginal polytope is then constrained by a set of half planes. Then the number of such kind of half planes is called the facet complexity. Then, however, for a general graph, this facet complexity would grow so fast, and it would then be very, very hard to characterize the marginal polytope. Therefore, we want to introduce some variational method, and that's our intuition. That's our motivation. And then, as shown before, the dual form, the dual function takes this kind of form, and then the exact variational formulation is like this. And then, where this M is the marginal polytope, and this A should be the this A star should be the conjugate dual. And then, as discussed, the marginal polytope M is difficult to characterize, while the conjugate dual has no explicit form. So to approximate this kind of marginal polytope M, there will be two commonly used methods to approximate M. One is the mean field method, and one is the Bethe approximation and the loopy belief propagation. So for the mean field approximation method, it is a non-convex inner bound for the exact form of entropy, and for the Bethe approximation and loopy belief propagation, it is actually a polyhedral outer bound, and it is a non-convex Bethe approximation. So in the following, we will just focus on this mean field approximation. So when we consider this exponential family with sufficient statistics phi defined on an arbitrary graph G, then the set of realizable mean parameter set is this one, this mg phi. And then the idea of the mean field approximation is to restrict the P to a subset of distributions associated with the tractable subgraph. So for instance, now we have this graph, which is this set. This is intractable, and then we can restrict it into a subset of this graph. For example, we can use this F0, which has this formula, and this will be a tractable approximation. And we can also consider this one, this T graph. This is also a subgraph of the original graph, and this is also a tractable one. So, that's how this idea works. And then we have the mean field method, which is for a given tractable subgraph. Then we consider a subset of canonical parameters like this. And then we use an inner approximation, which means that this MF phi is a subset of this MG phi. So we use the inner, that's why we say it's an inner approximation. And then using the mean field method, it can solve, we can solve this relaxed problem, this MFG problem, instead of the original instead of this original problem. So by doing this, these sets will move from intractable set to a tractable set, which would make things much more easier. And the mean field optimization is, we should know that it is always a non-convex for any exponential family in which the state space Xm is finite. So this is easy to explain. It's because recall that we have the marginal polytope Mg, which is a convex Hall like this. So we know that this outer part is this Mg. It's a convex part. It's a convex Hall. And then we require this MFG to contain all the extreme points of this polytope. So these are all the extreme cases we should contain in MFG. And then it is also inside this convex Hall. This would imply that this MFG must always be non-convex as long as this MFG is satisfy these strict subset conditions. And that's actually for the mean field approximation. And that's basically all the important things we should know about the variational inference. And now let's quickly went through these contents and summarize our today's reading group. So we should know that for the variational inference, first we have a very high level idea of variational inference. We should note that the variational inference is actually trying to re-express a quantity we care about by using a solution of an optimization problem. Then we use the latent Dirichlet allocation as an example. So this latent Dirichlet allocation is for a topic modeling problem. So we use this as an example and see how we can use the idea of variational inference to solve the real-world applications. And then we go to the practice of the variational inference. We introduce the stochastic variational inference, and then we introduce the black box variational inference. And then finally, we move to some theories about the variational inference, in which we provide a very general framework of solving a problem with the variational inference idea. And we also point out one of its existing problem is that the restriction field is the restriction set. The restriction set is sometimes very complicated, and then we consider what we should do, and then we introduce the mean field inner approximation to approximate this marginal polytope, and then to make the whole problem easier to solve. So basically that's everything for the variational inference topic. So please let me know if you have any questions. Thank you.